Thank you. My Italian is too limited to give the talk in Italian. Pero posso parlare pochissimo. I'm going to try to talk to you about the origin and evolution of life and why it is beyond physics. It's based on physics, but beyond physics. So I'm going to start. If I stand up, can you hear me if I stand up? Non puoi udire? Puoi udire? Migliore? Allora. So I want to begin by, so the first thing to tell you is that nobody knows how life started. So anything any of us who work in the field say to you is a theory. So I will say theory. Mathematically, the theory I will tell you is absolutely solid. Whether or not molecules behave the way I hope they do is another matter. Okay, here's the first part of the mathematical theory. Start with a number of dots. So here's a dot, a dot, a dot, a dot, and they're connected by lines. Erdős and Régnier in 1959 asked the following question. Take a fixed number of dots and connect them at random with lines. So think of them as buttons and threads. Put down 1,000 buttons on the floor, pick up a spool of red thread, break off a piece of red thread, tie two buttons together at random, and just keep doing that. Every now and then lift up a button and ask, how many buttons do I lift up with it? It goes through the most stunning phase transition. Where there's a lot of buttons and very few threads, the buttons form separate clusters called components in a graph, like here. When the ratio of threads to buttons is 1/2, 10 over 20, the number of ends of threads is equal to the number of buttons, because every thread has 2 ends. At that point, the phase transition happens, and a giant cluster emerges. And you can see it here, and you can certainly see it here. Most of the buttons are now connected to one another. They become more and more connected as more and more buttons are randomly connected by threads. The intuition I want you to take away, that almost nobody knows this, but now you do. If you have a large number of buttons and you connect them at random by threads, all of a sudden, wham, a bunch of buttons all get connected to one another. It's called the Erdős-Régnier phase transition. I'm going to depend upon it. We're trying to ask how we get molecular reproduction. So in 1971, I published a paper on the topic, and I still rather like it, in part because it's my idea, and that's all right. So here's the idea. Proteins are linear polymers of several kinds of amino acids. In the simplest case, there are 2 kinds of amino acids, say alanine and glycine. So think of a polymer that's alanine, alanine, glycine, alanine, glycine, 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 alanine, or so on, for some length n. Now, I want to consider the following system. I've got polymers. They can glue together. They can ligate, or one polymer can break apart into 2 fragments from which it came. So it's a cleavage reaction going to the smaller ones, or a ligation reaction going forward. Then I want to ask the following. Is it the case, or might I imagine, that these polymers can not only undergo reactions with one another, but the very same polymers might catalyze the same set of reactions? So what's catalysis? You know there are chemical reactions. A catalyst is a molecule that acts to speed up some chemical reaction. So I can catalyze a reaction in which Bill and Joe glue together. So I've now acted as a catalyst for the ligation reaction of Bill and Joe. It's now a mathematical theorem that the same Erdős-Régnier phase transition happens. Let me give you the spirit of it. If you make enough molecules in a pot, the number of reactions among the molecules is very large. Then you imagine a simple model of what polymer will catalyze what reaction. The simplest model you could possibly make is that every polymer has a fixed probability p of catalyzing each reaction. And then you just try it and say, is it the case that there's a set of molecules in the pot where each molecule gets the last step in its formation catalyzed by some member in the set? So I might catalyze Barbara's formation, and you might catalyze my formation. So we're a collectively autocatalytic set. The important thing here is that in this case, Barbara, or for the rest of us. I've used Barbara without her permission. So notice that in the case that I catalyzed Barbara's formation out of Barbara parts, and Barbara catalyzes my formation out of Stuart parts, neither of us catalyzes our own formation. Collectively, we catalyze one another's formation. We are a collectively autocatalytic set. And what I showed in 1971, and it's now a theorem and it's perfectly solid, that if you have enough molecules in a pot, with some probability p that any molecule catalyzes any reaction, you will get a collectively autocatalytic set that just pops into existence just like the Erdős-Rényi phase transition. I can show it to you in more detail if you want, but we don't have too much time. And here is one. So this is a graph. It's a special kind of graph. There's two kinds of entities in it. Circles go around molecules. They represent molecules, and dots represent reactions. So BAA plus BAB go through the reaction here to form BAA, BAB. So this is what's called a bipartite graph. Every dot has inputs from circles, and every circle has inputs from dots, reactions and molecules. But there's another kind of line here. This dotted line means that the molecule AABAA catalyzes the reaction by which BAA and BAB join together to form BAA-BAB. So if you examine this in detail, and we don't have to, it's a collectively autocatalytic set that popped into existence in a computer simulation of the kind I'm talking about. So just take it as mathematically true, because it is, that this happens, it's reliable, and the theorems are nailed down. Now let me tell you what the facts are. People have been trying to get molecular reproduction for a long time. A standard view about how life started is that there's an RNA molecule which is able to catalyze its own reproduction by being a polymerase. It's able to copy itself one nucleotide at a time. It has never worked. It might work, but it hasn't worked. What has worked are collectively autocatalytic sets. So they've been made out of DNA by Gunther von Kaderowski in 1994, out of proteins. This is really important. People think that life must be based on the template replicating properties of DNA and RNA. They're wrong. Proteins can make collectively autocatalytic sets. Gunan Ashkenazi has a 9-peptide collectively autocatalyc set in Ben Gurion in Israel. So peptide 1 catalyzes the formation of a second copy of peptide 2. Peptide 2 catalyzes the formation of a second copy of peptide 3 around the cycle, 9 doing it for 1. So it's a collectively autocatalyc set. Finally, Niels Lehmann has taken a set of RNA molecules called ribozymes, cut them in half, separating the catalytic site from the recognition site, put them in a pot, and it spontaneously forms a collectively autocatalytic set. We're getting very close to the spontaneous formation of collectively autocatalytic sets. We're not there yet. That's because Niels used highly evolved ribozyme RNA molecules. Right now he's trying to randomize those and see whether or not we get collectively autocatalytic sets. Okay, so we're doing okay on time. So I've now told you how to get molecular reproduction in a well worked out theory. It hasn't worked yet experimentally. I hope it will in the next few years. It may have now. We will see Niels Lehmann in 2 weeks in Vienna, and he'll tell us what's happening. Now, I want to ask a question that nobody's asking, but there's no reason not to ask it. Your metabolism has hundreds of kinds of small organic molecules in it. Each molecule undergoes a reaction that makes some other small molecules. Every reaction is catalyzed by some specific protein. So it's this huge connected catalyzed metabolism. Where in the world do we imagine that a connected metabolism came from in the origin of life? It's no good just having a single RNA molecule that's reproducing itself. It's nude. It doesn't have around it a connected catalyzed metabolism. I'm going to tell you what people sort of think. They sort of think it could have started one molecule at a time. There was some reaction that was catalyzed by some enzyme, and it has a substrate and it has products. Then maybe, an enzyme could come along that catalyzes a reaction involving the substrate or the product of the first reaction, and you could build up a chain of reactions that way. That might be right. On the other hand, maybe it's the same Erdős-Rényi phase transition, and we can think about this. So this is a working body of theory. It needs real theorems, but the theorems are fundamentally okay, so you can trust what I'm telling you about 98%. So this is a catalyzed reaction. This is a reaction graph. as before, dots represent molecules. Now squares represent reactions. So that's the molecules A and B go through a reaction to make C and D. So little squares are reactions. I've used black arrows to represent reactions. Black means the reaction is not catalyzed, it goes slowly. That's an idealization, but catalysis mixed reactions go much faster. Now, suppose that magically I throw at the system some catalysts. I'll tell you how in a moment. And suppose that catalyst 1 catalyzes the first reaction. I'll then color those arrows orange, not black, meaning they're catalyzed. And that reaction is catalyzed, and that reaction is catalyzed. Well, your eye is picking up that there's 3 little orange things, but they're not connected to one another. What happens if I just catalyze more reactions chosen at random? Well, you get that. You get a big connected random catalyzed thing emerging. It's emerged as the same air de Chaudière phase transition. I think you can see it happening in front of you. So my question becomes, did metabolism and the formation of a connected metabolism in early life happen as an air de Chaudière phase transition? I want to think that maybe it did. That I want to think that the candidate catalysts are themselves the molecules in the collectively autocatalytic set. So here it is. Here's my collectively autocatalytic set. And I've drawn four yellow arrows here to show that the peptides in the collectively. Okay? Manage. I understand that it's not too bad to say manage. So there's 4 yellow arrows coming out of the collectively autocatalytic set, 4 peptides that are catalyzing 4 of the reactions. There's some more arrows coming for the other reactions. That's great. Now the collectively autocatalytic set is catalyzing the molecules in a metabolism, but the metabolism is not yet helping the collectively autocatalytic set. If only they could help one another. Can they? Well, of course they can. All we have to imagine is that the molecules in the connected metabolism serve as substrates for the collectively autocatalytic set. And now both of them are together. I really think this is perfectly possible. In fact, I'm kind of in love with it. I don't know that it's right. At least it's creative, and we're here for creativity, so at least this is a creative thing. So now what does that give us? Well, to put this inside of a liposome, so I have to tell you what a liposome is. If you take lipids and put them in water, they form hollow lipid vesicles, a little bit like soap bubbles, except that they have 2 layers. It's a bilipid layer, and they're about a micron across. And everybody likes the idea that early life was somehow inside of liposomes, which would have confined the reactants to a small volume so it didn't diffuse all over the Atlantic, and given them an inside and an outside. For that, we have to imagine that our metabolisms make some lipids. Well, okay, we can imagine that. So here it is. So this is my protocell. The purple are the lipid membrane. The metabolism makes lipids. The cell takes in food over its boundaries. Here's the metabolism. Here's the collectively autocatalytic set. And these things will, in fact, liposomes can actually grow and divide by themselves, a little bit like forming bubbles in the bathtub, and they get bigger than they could break into 2. They could squeeze into 2. It's the same thermodynamic process. Roberto Serra here in Italy has shown that if that happens, the 2 divisions synchronize with one another. The liposome synchronizes its division with the collectively autocatalytic set. So it ought to be possible, and my deep hope is that in the next 10 years we're actually making protocells, perhaps rather like this. So that gets us to protocells. This is just an enormous transition. If we could get this far in the next 10 years, we would be really, really happy. I don't have time to tell you this, but at the end you want to hear about David Deamer and Bruce Damer and their stuff. I'll tell you. It's a beautiful set of ideas. So, I have enough time. I've got 5 minutes. That's a lot of time. I want to tell you a true story. This happened, it's a children's story. And it's absolutely true. It happened 3,493,675,228 years ago on a Wednesday afternoon on a small rocky promontory in Western Australia, or what would be Western Australia, in a geyser. So there's a lagoon, and there are protocells in it, just like the protocells we saw. In fact, this is a story of Patrick, Rupert, Gus, and Sly protocells before they became Patrick, Rupert, Sly, and Gus. Well, they're in the lagoon. And the lagoon, you see, has slowly flowing stuff. You can see that stuff. It's stuff. Okay, it's flowing. And Patrick and Rupert and Sly and Gus bobble around in the lagoon, and they eat stuff. And they divide, and they're perfectly happy. And nobody's mad at anybody because they all get enough stuff. So they're perfectly content. Well, do you know what happens to Patrick one day? Can you guess what happens to Patrick? Well, of course you can't. Well, Patrick feels a bump inside of his tummy. And he says, "Oh! Oh, what's that? Oh, no. Oh, it's my whatchamacallit." Well, a peptide sticks out of his tummy. It's 13 amino acids long. "Oh, no," says Patrick. "It's outside of my tummy. It's a hole in me." Then do you know what happened to Patrick? His peptide got stuck to a big rock. Patrick, so there's Patrick, and he's stuck to a rock. And Patrick says, "Oh no, I'm stuck to a rock. I don't want to be stuck to a rock. I want to be floating free in the lagoon, getting stuff like everybody else. If only I had a mom, I could call her and tell her, but I don't even have a mom." Well, then you know what happened? Patrick looked around him, and because he was stuck to the rock, he saw food rushing at him from one side and then the other, and one side and then the other, because he's not moving and the stuff is moving inside the lagoon. But he's stuck. So he gobbles and he gobbles and he eats and he eats and he eats and he eats and he eats, and he, guess what? He divides sooner than he would have before. So pretty soon, it turns out his kids are stuck, and they're stuck to the very same rock. Well, what has Patrick become? Patrick has become Patrick, the very first sessile filter feeder in the universe. That's what's happened to Patrick. He's become a sessile filter feeder. And he gets more food than he would have otherwise, and thanks to heritable variation and natural selection, you can get heritable variation and natural selection here. Pretty soon there's Patricks, and they're growing in a Patrick patch, which you can see here. That's Patrick's in the Patrick patch, in the whole lagoon. They're all kind of close to one another. Which brings me to Rupert. Well, Rupert is sort of an ordinary protocell, except for the fact that Patrick can't eat anybody, but Rupert can already eat other protocells. He can go and poke a hole in them. He thinks that's really great, because every now and then if he bumps into another protocell, he gets an extra dinner. But that doesn't happen very often. They're all floating at the same speed in the lagoon. Well, one day, Rupert floats into the Patrick patch. Rupert is just miserable being in the Patrick patch. He says, "I don't want to be in the Patrick patch. I want to be out in the clear lagoon with everybody else and all my friends." And he says, oh no. Well, then you know what happens to Rupert? He bumps into a Patrick. Well, Patricks are not moving. So Rupert can find Patricks really easily compared to finding free-floating protocells. And what happens is Rupert pokes a hole in Patrick the 4794th, who says, "Gah!" And Rupert says, "Cool." Rupert thinks that's really great. Well, Rupert can have heritable variation and natural selection, so pretty soon there are Ruperts who are growing on the Patrick patch. Well, Rupert has become Rupert Raptor Protocell. Raptor Protocell. He's the very first predator in the universe, and this is the very first food chain in the universe. Now, isn't that all pretty wonderful? So I could tell you about Sly and Gus, but I don't have time. So let me just sort of tell you what I think we've learned with all of this. Do you think this room is filled with people who also like to make mathematical models, including me? We're all busy being mathematicians and scientists. Do you think you could write down equations that would predict the occurrence of Patrick or Rupert? You don't even know what the relevant variables are. You don't know that Patrick is going to get stuck to a rock and become the very first sessile feeder. You have no idea how to write that down in your equations beforehand. Do you think you could make an agent-based model, as in the form of agent-based models that's algorithmic? I don't think so. I think something is going on that's just amazing, and it is the innovation that we're talking about in this conference. Patrick and Rupert just innovated, and they innovated in a way that cannot be said ahead of time. Afterwards, we can make sense of what happened to Patrick and Rupert. Furthermore, what I've just told you is the exact truth, except for the fact that I made it up. Something like that happened, and I promise you that something like that keeps happening all the time in the evolution of the biosphere, which has the property that as it evolves, what are called Darwinian pre-adaptations, exaptations, keep happening, and nobody can say ahead of time what they're going to be. We cannot mathematize it. We can write down no laws of motion for the evolution of the biosphere. We cannot integrate the laws that we don't have. Therefore, no laws entail the becoming of the biosphere, including Patrick, Rupert, and Sly and Gus, who are a little sad because I didn't tell you about them. That means that life is based on physics, but it's utterly beyond physics. Thank you.